Hello and welcome back. This is part 3 of the Commodore 64 assembly language programming series, where I take a look at the basic examples, the basic programming examples that were given at the Vintage Computer Festival East 2023 Commodore Classroom and try to convert them into an assembly language counterpart. Once again, my name is Jeff Salzman, and once again, this is a stream of consciousness recording. You'll hear sounds in the background. I may pause the video. You won't notice a difference until the sounds settle down. So, getting started, I want to show the program I'm going to work on this time. You can see here there's one called Animation 1. Now, this one defines a variable. Gives it a value of 50. Then it goes through 4 iterations of creating a character in a variable and then going through a subroutine. Now this, I actually had this preloaded into WinVICE with the PAL Power. The PAL assembler already loaded up into it, so I'm all ready to go. But this is the basic listing here. Let me switch to it and list. So this is the same program. And so it starts out D equals 50, then sets the C string variable to one of 4 values, and after each one it does a go sub 100, and then it goes back to line 10 again to continue. So when the go sub 100 is reached, it prints the value of C with a semicolon. That means it's going to print and then move the cursor 1 to the right. Then it prints the equivalent of character number 157, also with a semicolon. So it moves the cursor and prints again beside the previous character. Then it does a for loop for C equals 1 to D, next C, so I guess it's using the value of D to create a timing, a pacing loop. I guess if you increase the value of D, it'll animate slower, and if you decrease it, it'll animate faster. And then this is the return to go back to where the go sub 100 was called. Now, this value here is actually the left cursor. So it will print whatever stored in the C string variable and then press the left cursor to go back. But let's just run this right away and see what it does. You might already have an idea. If I run it, it just spins something around. The 4 characters used represent the animation frames of a spinning line. Fairly easy. Just shows you what you can do with printing and the keyboard control, that you can print actual keyboard values. So I'm going to stop this and list it again. And just like the last video, I'm going to keep this and then add my assembly language code below it somewhere. Right now, as this program will only go to line 50 and return back to line 10, and then passing through the subroutine at 100 through line 100 through 130. But just in case, I'm going to put a little safety stop in here and use the stop command, or stop basic keyword. That way, if it does somehow pass through it and we run this, it'll just stop at line 140 on its own. I don't think it'll ever reach that. But for the sake of mixing source code from the basic and assembly language version of this, that's just kind of a safety block. So, and I'm not bound by line numbers for the assembly language, just like you're not bound by specific line numbers for basic. We just have, we start, favorably with line 10 and work up. So I'm going to start using line 1000 here to build my assembly language source code. And just like the other videos using the PAL assembler, we need to start our assembly language code with assist 700, followed by some options. In this case, same options I used before. We're going to print the source code out as it compiles, and we're going to compile it to object code right in memory. And here we'll define the starting point in memory by setting the program counter equal to C000, which is equivalent to 49152 in decimal. So looking at the source code, let me switch in here. So looking at the basic source code, I have to make a decision right now, and for now I'm not going to worry about setting a timing loop. I can put one in later, but right now I just want to get the action to occur and not time the action. So I'm not going to try to do anything like set D equals to 50 or the assembly language alternative to that. But I will start a loop. In the basic version, the loop starts at line 10, and line 50 tells it to go back to line 10. So I will set a start label here, actually line numbers. I'll set a label called start, which is equal to the program counter at this point, which will be C000 in this case. And then to pick out the 4 values that I need, the 4 different characters that I need, I can make this, I can write this where it'll load the accumulator with the character value of the first graphic character, and then use call FFD2 to call the character out in the kernel, and do that 4 times. But it'll work. That'll work just fine. But what if I wanted to change the characters to something else later, try some other spinning effect with other characters? I will use basically like a lookup table. I'll use indexing to go through 4 separate characters that are stored elsewhere in the source code, and we'll just traverse through them 1 through 4, 1 through 4, 1 through 4, or 0 through 3, should I say. So before I build that into it, I need to plan ahead here. So I'm going to count through 4 values in RAM. So I'll set up a counter. 1040, I'll load the X register directly with the value 0. So that'll be my counter. I'll use the X register for the counter. And actually there's the start, and then this is where my loop's going to start. I was like trying to think far ahead on this as I write it. There will be a possibility that I'll have to reset X to 0. So the start label will take the code when I go there to reset the X value to 0. And then here I'm going to do my looping. I'm going to set a loop label equal to the program counter at this point. And then this next block of code is what I'll loop through until I need to reset X to 0 again. Now there's other ways of doing this. I'm just doing it this way because it does demonstrate some concepts of assembly language programming. So I'm going to define a label which from that point on in memory will contain the values I need. I'm just not defining those values yet, but I will use the label to reference the location in memory that I'm going to get that. So first thing I want to do is get the first value, like line 10 of this basic version. I want to get the character value for the vertical bar. So, or I want to get the first character. So I'm going to load the accumulator, and I'm going to name my sequence of memory that contains the characters I want to print. I'll call it CHARS. That'll be my label. I will define that label later. But wherever this label is at, that's where it's going to start looking. And we did this in, I think, the first video. We used an offset of X, or indexed by X. So X is 0 now. This first time around, it'll call the first location in our memory with the label CHARS. I'll just kind of abbreviate that characters. So we're going to load the characters, the first character, and then we'll send it to the screen using the kernel call JSR, using the character out, which is JSR $FFD2. Now, in that Go Sub 100 in the basic version, you see that it prints the character that was selected. We're just doing it a little different. So we load the character up into the accumulator. We print it out using the character out. But then we need to print another character. You see line 110 in the basic version. We need to print the character 157. So this is actually pretty easy. So I'll do line 1080. We're going to load the accumulator again, but this time we're going to load it with an immediate value, and I'll use the decimal form for now for ease of use, number 157. That is the equivalent of the left cursor key. And once again, we'll print that out by calling JSR FFD2. So we load the next character, print it, load the cursor left, print that, which then moves the cursor back into place again to print the next character, just like in the example for basic. Now at this point here, I'm going to make it loop, but I want to be able to stop this at will. And since we've at this point of code printed the character we wanted to print, and then backspaced over it, or left cursored over it, now would be a good time to check to see if we press a key to exit the machine language program. So just like in the previous ones, I'll do 1100. We're going to make the call to the getIn kernel call, and that was JSR FFE4. And as mentioned in the previous two videos, when this call is made, the accumulator will have a value. That value is either going to be the value of the key from the keyboard item that was pressed, or 0 if no key was pressed. And we don't care about the actual contents of the accumulator. If the accumulator is 0, it's going to put the registers, the status register in the 0 state, and we're going to check for that like we've done before. 1110. So we're going to branch if not equal to 0. And I'll create a new label ahead of time to where we want to stop the program, and I'll just call it end run. That's going to be my label. I will define that later at the point where I want it to run code to stop the program. So if we hit a key, then the accumulator is not 0, and the 0 flag has not been set in the status register. So this will jump us to the end run because we have more to do to work this loop. We're done with this value of X, so we need to increase the X value, 1120. So we'll increase X. That'll bump it up by 1. And now we're going to do a comparison. We're going to see if X is going to start at 0, it'll loop through 4 times, so count from 0, 1, 2, and then 3. If X reaches 4, we need to reset the X register back to 0 again. So we're going to compare. This is, I think, a new opcode that we're using. It's called CPX, compare X to something. Now we can compare X to the contents of a memory location by putting its memory location here, but we're just going to compare it to a specific value. So again, immediate addressing mode, we're going to compare it to the number 4. If X counted up and is a 4 right now, we need to make it a 0 and then continue on with our program. So if the comparison matches, here's another thing. I've told you about zero states before. When any kind of action in the microprocessor creates a zero state, then you can test to see if it's equal to zero or not equal to zero. Well, in a comparison, if something equals something else, that also creates a zero state, if they're exact. So if x is 4, when we compare it to 4, that creates a zero state. And for that, we can branch if equal to our start location, which is up here. And that's why that start is in there, because then the next instruction will load x, it'll reset x back to 0 again. But if it's not 0, then it's going to run, or if it's not equal, then it's going to run the next line here. And for this, we're just going to directly jump to where we put the loop label, which is on the other side of setting x to 0. So this will just keep jumping through and keep running as long as we don't press a key here, and as long as x is not equal to 4, it'll determine which loop, which point of the loop it goes back to. So this is our main program. Now we need to tie up a few ends. For one, we still have to deal with that end run branching up in line 1110, and we can put that right here. 1160. We can set the end run label here equal to the program counter at this point, and then 1170, we'll put an RTS. That will stop the program when a key is pressed up here. It'll branch to end run, it'll go here and execute the RTS, the return from subroutine, which basically ends the program at this point. Now, we still have to define the characters and which characters we're going to use. So we used up here, we used the label to indicate where the program can start looking for characters, and we have to set up 4 bytes of memory that contain those characters in sequence the way we want to display them. So at 1180, we'll define a new label called for characters equals to the program counter, and then here's a new compiler directive, 1190. You can actually insert fixed values in the compiled stream of data by using the byte directive. And what this means is anything following the byte directive, separated by columns, is a series of numbers which will represent the values you want to store from this point on in memory when it compiles. So which ones do we need? We can see on the we switch back to here. We can see that we need the vertical bar, we need the / graphic character, not the / type character, a horizontal bar, and like a reverse /. So going to the Programmer's Reference Guide here, which has our information. Let me go to it. In our Programmer's Reference Guide, we can see what those codes are, and we did this in a previous video. It's back in one of the appendix pages. I don't know if it was appendix A. Yeah, I think it was appendix C here. Okay, so here's our printable characters, ASCII and CHR $ codes. So the first one is a vertical bar. And looking here, I see the vertical bar as number 98 in decimal. So we'll keep that in mind. The next thing we need is like a / graphic, and I see that here is 110. And then we need the horizontal bar, which looks like it's 99. And then the reverse / graphic, which is 109. So those are the 4 that we need. So going back here, we're just going to put those values in here. We're going to put, the first one was a 98. 98, comma, 110, comma, 99, comma, 109. I'm actually using the decimal values. I did not precede any of these with the $sign, so I'm using the decimal values, and hit enter. So when it compiles this, it will reserve the last 4 bytes of our program to store those specific values. So when this code runs here, load the accumulator with, starting at that memory location that's labeled indexed by X. If X is a 0, it'll pick this up. If X is a 1, it'll pick this up. So each of these values gets loaded into the accumulator in turn. And then after this, this is X equals 3, or X is 3, X will become 4, and then this comparison here will cause it to go to the beginning of the program again and reset X to 0 and continue the loop. Not a big program, just it's written out a little different than the basic is. So I'm going to list this again, and we'll see the basic version and our version separated solely by the line numbers. So in order to compile this, I have to do a run 1000, not 10,000, 1000. That'll then execute the sys 700, and everything left over will be compiled as assembly language or machine code. And it went through cleanly without any errors, which is good. So let me run the program by itself, which will run the basic version. See how that's spinning with a small delay, with a loop count of 50. I'll stop that, and then we'll run. I'm still using the same starting location as I did for all the other videos. sys 49152. It's much faster, isn't it? I don't know if you're seeing the spin the way I saw it spin before, but it is a lot faster. There could be some tricks with the frame rate of the recording that makes it look like it's running slower because the timing's just that much, in or out of sync, but it is spinning a lot faster, and it is running in machine language, and it should respond to a key press to stop. Let me list this one more time and put it up beside the one-liner. Well, not one-liner, we did the one-liner last one. Put it beside the original source code that was called Animation 1 in the Commodore classroom. Didn't take long to write this, but you do have to, in writing this, I had to kind of keep in mind that we're going to set up locations in memory where we're going to jump to, we're going to branch to, and where we're going to pull data. So this, we could substitute any other values in here. Let's look at that. Let's try something real quick. Let's see if we can't find something that might look better, different. So I'm going to bring up the Programmer's Reference Guide again. And what characters, when animated, will look pretty good? We could probably do this X here, 118. And we could probably do this plus 123. Or we can do these quarter blocks here. We can make those spin around. Let's do the X and plus. And I'm not going to go into great details on shortening the amount, how far we're going to count or whatever. I'm just going to repeat these values twice because we need 4 values. I'm just going to put 118 followed by 123 followed by 118 followed by 123. So getting back to that, and I'll just keep it on the screen here. I'll go back and edit this line here. So what did I say it was? 118 followed by 123 followed by 118, followed by 123, and it should loop from that. So running at 1000 will recompile this with their new values, and sys 49152 just switches between them. So this is a technique how you can use a lookup or use an index to look up values that are going to be processed in sequence. In this case, I had to know what values I wanted to process in sequence, but those were easy to find, especially for what I want to do with them. So there it is. Once again, if you have any questions, you can leave comments in the video down below. You can also contact me through my vintagevolts.com website, or even on Twitter @vintagevolts. Meanwhile, have fun programming.